questions. The first one, when we evaluate a general polynomial, do we have multiple ways to evaluate? Yes, but at least we have two ways, right? One is the brute force. Second is the Horner's rule for the general case. Okay, yeah. Easy question, yeah. The brute force and Horner's rule. Yeah. Repeated squaring, yeah. Actually, yeah, you can say, yeah. All right, so let's see. Look at this. So the brute force, one, Horner's rule, yeah. Because we apply repeated squaring and repeat cubing on monomial, and when we calculate polynomial, we can, only when we calculate monomials, we call repeated squaring, repeat cubing. So those two, okay, yeah. So we can also say different methods, yeah. All right, based on. Because there are two, based on repeated one squaring, another cubing. Okay, yeah. That's those we used in this class. But people can find more, okay? Yeah, more. For example, yeah, Pascal's triangle, that's not for the general case, okay? So here we're talking about the general case, not special case. Yeah. All right, next question. Since the linear search is too slow, yes, it's very slow. We agree with that. Yeah, it is basically useless to solve any real-world problem. That's false. No. It's still useful. Yeah. The reason is simple, because in the real world, many times we have unordered array. We have unordered data, yeah. And you have to do the search. You have to do the search. Yeah. So then you can only use the linear search. Yeah. We know it's slow. Yeah. But the problem is sometimes we have unordered array, but the length not too large. Yeah. If the length of the array, okay, or array size, yeah, let's say array size. If the array size is not large, yeah, then we just apply the linear search. We do not sort it, okay? Yeah, we do not sort it, yeah. Because if you sort it, the extra work you use may not worth the binary search, the work you can save. Okay? But if the size is large, then worth it. Yeah. Then it's better to sort than you apply binary search. Especially for many times. Yeah. If you do it for the many times. Yeah. But because sometimes we need to sort array not that large. Yeah, not that large then. So if you sort it, yeah. Oh, yeah. So two factors you do not sort. One is the array size is not large. Another factor and only do once, okay? do search once, not many times. If you many times, it's better to sort, okay? But you only do search one time, okay? Then you throw away the data, so then you work on a different set of data, right? Yeah. So for this situation, you do not sort because not worth it. Not worth it. Extra work you do in sorting, you cannot save the same amount of work. No. The amount of work you save not worth the extra work you put there. Yeah. Yeah. So that's about the linear search. Just still useful. Yeah. All right. Number 3, when we solve some computing problems, sometimes it's a good idea to work on a few cases with small data sizes, do experiments, right? Yeah. So we applied this strategy many times. So here I just described that a strategy we use frequently in this class. Yeah. Then we can extend our solutions to the general case. Yeah. Because after we have some experience, yeah, especially we can observe some properties, then we extend the property to the general case. Yeah. All right. Yeah. So you can see some questions are pretty easy. Yeah. Yeah. All right. Is the stable? Yeah, not stable. Okay. We talked about it in class. Not stable from hardware and software. Right? So we look at that question. From the hardware side, not stable because people use different computers, different machines. Okay? When you use different machines, the response time different. From the software side, when you write programs, you may have different implementations. That will cause the different response time, different implementations. Okay, yeah. Not stable. So we do not use this way. So in our analysis, we use the counting number. We count the number of basic operations. So that's a stable measure. All right. Number 5, in order to derive Horner's rule polynomial, which of following mathematical operations is useful? Factorization. Right? Yeah. So you can see the success, the key to the success, a special factorization. A0 plus x times A1 plus x times A2 plus and so on. Okay? Yeah. Yeah. The last an minus 1 plus an x. This kind of, factorization. Yeah. So this special factorization, why we can save a lot of multiplications. The reason is simple. That the reason we can save a lot of multiplication. Here, the main reason we can save up. So that is because we can share many multiplications. Okay? For example, this multiplication we share with many terms we share. Yeah, but here we only do one, right? This one we also share, with all the remaining terms. We only do one. One covers many. Yeah. So this one covers, let's say, covers n terms. N term. This one covers n minus 1 terms, and so on. The next one, n minus 2 terms. Okay? Yeah, so you can see that's the reason we have that efficiency. Okay? Yeah. So one multiplication can be reused. You can look at it in this way. That particular multiplication actually can be reused, for many terms. Many terms, if you do not reuse, you need to do many times. Yeah, but that kind of reuse. Yeah. So we group them. So we group those terms. Then we apply 1, but that one takes effect on all those grouped terms. Yeah, we understand in that view, so we can say, yeah. All right. Yeah. So then, this question, yeah, because one student asked me the homework question number 1. Homework question number 1. Okay. Yeah. Then you need to connect to this. Okay. You need to connect to this structure, this factorization structure. X cubed, right? X cubed factorization, x to the 4th, yeah. X cubed, x 4th, all right. When you calculate, so for this question, x to the 4th, x cubed, in your preparation stage, you need to calculate these two, okay, 2 numbers. That's the preparation stage. But when you calculate, think about, reuse the resource. That idea. Reuse the resource is our multiplication. Okay? Reuse the resource. Resource is the results from the multiplications. So reuse resource. All right? Yeah. For example, when you calculate these 2 numbers, do you need to know x squared? Yeah. You need to use x squared, intermediate result. X squared, can you save it, store it in a temporary variable? After you calculate x squared, do not throw away. Okay? Yeah. After you calculate x squared, because x squared is useful, is your resource. Yeah. So you can use x squared to get x cubed, also x squared to get x 4th with the minimum number of multiplications. Yeah. All right? Yeah. Thinking this way. But that's the preparation stage. All right. After you complete your preparation, then you evaluate the whole polynomial. Remember this factorization form. Okay? Whole polynomial in similar to this form. Yeah. But x cubed is known, x to the 4th is known. Do not recalculate them anymore, right? So use 2 variables. x3, for example. So here, let's do this one. x2 we start in var0. Okay? The first variable, var0. X cubed, we store it in var1. X to the 4th, we store it in var2. Okay? After you store them, you can reuse, right? Do not need to recalculate them. Okay? Then, when you calculate this polynomial, when you see x3, use var1. Okay? Copy the value from var1. Okay? So we do not count multiplication, because that assignment is very fast. We do not need to spend it up. The assignment operation, very fast. Okay? Even faster than addition. The assignment faster than addition. So we don't worry about assignment operation. Okay? Yeah. So you just retrieve value from var1, then you calculate. Whenever you see x cubed, you use that value. All right? Then, inside you may need to use x to the fourth. Then you retrieve the value from var2, right? Then no multiplication needed. After you complete multiplication preparation, then whenever you need to use x cubed, x to the fourth, assignment operation. Just use assignment operation. Okay? Yeah. So no more multiplications needed. Yeah. But in the parentheses, these places, you need to do multiplications. Okay? Yeah. That you cannot say it. Yeah. You have to do new multiplications. Yeah. So in this way, you count the total number of multiplications for homework assignment number 1, question number 1. Okay? Yeah. 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 So use this idea. All right? Save as much as you can. Okay? Yeah. Yeah. When I do the grading, I based on how close your answer to the true answer. Yeah. Yeah. So if not the same, sometimes I can give you a partial credit. Okay? If your answer is one difference away from the true answer, I'll give you 2 points. Total 4 points. Okay? Partial credit, 2 points. The difference is 1. Okay? So here. So we have a final answer. Okay? But you choose one, just one away from the true answer. Okay? So I take 2 points off. All right. Yeah. That's that question. Number 6. When we apply the linear search on a given array, which of following types? Yeah. So that obviously unordered. Yeah. Ordered. Yeah. So the problem is this. Yeah. For linear search, you cannot get wrong, right? Even ordered, but if you do not know, sometimes the array could be ordered, but you do not know it. All right? Yeah. If you do not know it, you apply linear search on it. Okay? We know computer does not have eyes. The computer cannot see if you do not do the checking work, the computer cannot see the data is ordered. Okay? The computer does not know the data is ordered. Even the data is ordered, it does not know it. Yeah. So you still apply the linear search on it. Yeah. All right. I need to use this computer. All right. Yeah. But the other case people get it wrong frequently, that is when the data is ordered, not data is ordered. Yeah. People apply binary search on unordered. Yeah, that problem is, many people do this kind of error. So many people apply. So here I say the error case. Okay, yeah, error case. Apply the binary search on unordered data. Okay, they forgot to check. Yeah. They know. Okay? They know they cannot apply binary search on ordered data, but they forget to check. Okay. They do not realize they need to check. So this kind of error happens a lot. Okay. Yeah. Yeah. All right. But for linear search you cannot get wrong, right? Yeah. No matter it's ordered, unordered, always correct. Yeah. But for binary search, if you do this, you get a wrong result. Okay. Yeah. So yeah, not the wrong. So you do some garbage work. Yeah. actually. Yeah. All right. Number 7, easy. Answer C. Yeah. So you can see some question. I give you some very basic, simple questions. Yeah. So even in homework assignment, in tests, not all difficult questions. Yeah. Some questions very easy. Yeah. All right. This one, factorization. Okay. Yeah. So I hope you can see it. We can factor out 3 squared. After this factorization, inside you have 1 squared, you have 2 squared, you have 3 squared, you have n squared. But this part we have formula, right? Yeah. Given in the class 1/6 n plus 1, 2n plus 1, the formula. But now you multiply 3 squared and 1/6, so you get 3 halves. So 3 halves, then multiply the variable part. Yeah. Yeah. So you see D, right? Yeah. You see D. Okay. Yeah. And for question like this, yeah, if you know the formula, you use this way. Yeah. Yeah. But some students, if they do not know the formula, you just plug in some small n numbers and check it. First, plug in n equals 1. Yeah. Which formula can be eliminated? Yeah. Because plugging 1, you can get answer of that summation, right? When n equals 1, you know that number. Then you plug in, each of the formulas in the 4 given options and see which one can be eliminated. Yeah. If 2 numbers do not match, you can eliminate. But you cannot, if the numbers match, you cannot say correct. Yeah. Because 1 experiment is not enough. Sometimes you have more than 1 matching options. So if you do not eliminate all except 1, you need to keep doing experiments. So n equals 2, eliminate a few more, yeah, or 3, eliminate a few more until only 1 left. Yeah. Yeah. The correct one must be always correct. Yeah. The incorrect one, after a few experiments, then, yeah, no match, then eliminated. Yeah. So that's another method, yeah, by experiments. Yeah. Because sometimes I may give you questions, the formula not given. Yeah. The formula may not be given. Yeah. So, and in the tests, I do not allow you to use search engine to find the formula. Okay? I do not allow you to use the search engine to find the formula. Yeah. Then you can do experiments. Okay? Yeah. 1, 2, 3, and so on. Yeah. Usually you do 2 experiments, you can find the correct one. Yeah. All right? Yeah. Question?
Did you say we're allowed to use mental tests and equation sheets?
Yeah, let me repeat. The legal way and the illegal way to use your laptops in the tests. Yeah. The legal way, you can use your laptop to look at our study materials. Yeah. All our course materials, that's legal. Yeah. From Canvas, from your local computer, yeah. But for our course materials, that's legal, okay? Another legal, you can use online calculators. That's also legal, okay? So when you need to do calculation, yeah. For example, advanced calculator like Wolfram Alpha. Okay, so it's legal. You can use. You want to calculate logarithm, right? You know, some function. Yeah, any math function you want to. You know, yeah, that's legal. All right. Illegal way, search engine. You cannot use search engine to find the answers. All right. Yeah, any software, ChatGPT, you cannot. Okay, any software finding answers, that's illegal. Yeah. Another, any communication software sending messages, also illegal. Okay, yeah. So you cannot read messages from communication software, sending messages from communication software, all illegal. Okay, yeah. So that's the rules for in our tests. Yeah. All right. Number 9, answer is yes. Yeah. So this question, you need to, yeah, this I treat this as the hardest question in this quiz. Okay, the hardest one, because you need to put knowledge pieces, several pieces together, then you can get this answer. Yes. Yeah. First, special polynomial, okay? Not general. Yeah, special. You can take advantage of that. Yeah. Special here, what's special in your mind with n terms? Binomial. The special, I hope you connect to the binomial. Binomial, we just take 1 plus x to the n minus 1. This binomial. Okay? Because this binomial has n terms. Because the requirement, condition, n terms. N terms. Okay? Yeah. Yeah. N minus 1. Yeah. All right. Then, this binomial, n minus 1, no. But when we calculate the, calculate the number of multiplications, think about, we apply repeated squaring. Okay? Yeah. When we calculate, we consider the case. Consider the case. n minus 1 is power of 2. How about that? 2 to the kth power. Because in this way, when we calculate the repeated squaring, we need k multiplications, right? Yeah. So by repeated squaring, need k multiplications. All right? Yep, k multiplications. All right. Then, percentage, right? This percentage, that is, yeah, because this k over n. We want to see this k over n. Is it less than 0.03%? Okay, yeah. Think about that. Yeah. All right. Yeah. K over 2 to the k plus 1, right? Less than k over 2 to the k. Is it possible this number less than 0.03% when k is large? Yes, because this limit approaches to 0, right? When k approaches infinity. If it approaches zero, then it's very easy to beat this 0.03% number, right? It can be any given number, right? If the ratio, this ratio approaches zero, it can be any given number, small number. Any small number, when k is sufficiently large, you can beat it. Okay? Yeah. So you can use this limited view. Yeah. So that's why I say for this question, the hardest, because you need to put your knowledge of so many pieces together to make this puzzle. Yeah. Yeah. The whole question you treat it as a puzzle. Yeah. But you need several pieces, puzzle pieces of knowledge. Put them together so you get this correct answer. Right? All right, yeah. So that's the, the hardest one. Yeah. Some of you may just guess it. Yeah. If you by intuition, something answered by intuition. If you do it by intuition, it's very likely you feel no, because hard to imagine how to make it, right? Yeah. Some students, hard to imagine. How can I make it? Okay? Yeah. But some students can get the correct answer, but by the wrong logical reasoning. Yeah. Because if they miss the end terms, some students, they didn't pay attention to the condition end terms. They just treat one term. Yeah, one term. Then you can do it by repeated squaring. Okay? Yeah. Then you see it's correct. Yeah. So you pick the correct answer. But, you have some problems in your logic thinking. Yeah. That also happens. Yeah. All right. Yeah. So that's number 9. Number 10. Can we say greedy egg always give us? No, we cannot say. Okay. Yeah. Yeah. Always give us the best solution. Best solution we can understand as optimal solution. Optimal solution. That's the best. Okay? If it's not optimal solution, then people can argue there is a possibility it's not the best because other people can find a better one. Right? Yeah. Yeah. So let's assume we mean the optimal solution is the best solution. Yeah. But the greedy algorithm can only give us local best solution, not global best solution. Local, yeah. Because you only look at your data locally. You choose the best solution you can get. Yeah. You do not look at the data globally. Okay? Yeah. So then if you use the global view, then your solution may not be the best. And many times, it's not the best. Yeah. Only when in some special situations, your solution is best. Okay? Yeah. So you need to prove it, because it does not automatically give you the best solution. You need to prove it is the best. If you want to make that claim, you need to prove it. But in general, it's not optimal, the greedy strategy. But it is still useful. Why? Yeah, first, it's easy to use. Greedy algorithm, easy to use. Second, even if it does not give us the optimal solution, if it can give us near optimal, then we will be very happy, right? Near optimal, that's good enough. Okay? Yeah. So many times people are very satisfied if they can get near optimal solutions, slightly away from the optimal solution. Right? That's good enough. Yeah. All right. Yeah. So that's the quiz number 1. Yeah. All right. Then I need to move to homework questions. Hints part R1.2. Okay. Yeah. Because today we do R1.2. Yeah, next time we do R2, then R3. Yeah. Hints for homework assignment number 1. Yeah. First, these 2 questions are because Zach asked these 2 questions in the previous class. Yeah. So let me explain. Probably other students may have this same question. Yeah. So let me explain these 2 quickly. Yeah. These 2 questions, what Zach asked us is this in-place concept. Yeah. In-place concept. Yeah. Very, very simple. So what's the meaning in place? Yeah. We talk about in class. Yeah. So the right positions. Yeah. All right. So here, our goal. Yeah. So here, the goal. Sorted array. Okay. Yeah. Zach, I'm answering your 2 questions last time. Okay. Yeah. All right. So given an array, yeah. So let's imagine, yeah. You know, so we want to get the array sorted. Yeah. All right. So then, we say this. Yeah. Then. All right. All right. So after the array is sorted, so we treat the locations of the elements as the destination location. Okay, yeah, because you may need to change the original locations, right? So when you do the sorting, so move elements around, okay, swapping, you know, so change locations. So at the end, when the whole array is sorted, each element has its destination location, okay? Destination location, yeah. So in place means in place concept. In place here, when we talk about this concept for an element, okay? We talk about in place for an element. It means, the meaning of this is its original location equals its destination location, okay? Then we say it's in place, okay? All right. So here, is it possible to arrange these n elements such that all of them not in place? Okay? Yeah. All right. So here you need to imagine some input, special input. Imagine some special input. So here I ask you n greater than 7. This 7, I just want to make this n number not too small. Okay. Too small. Yeah. Because if too small, if n equals 1, that's impossible, right? 1, that element must be in place because you cannot move it. Okay? 1. So I don't want to include n equals 1. If n equals 2, then you can move, right? Yeah. Although I can say n greater than 1, but sometimes I try to hide something. So I use the 7. The reason I choose 7, I do not choose 1. I try to hide something, okay? Yeah. Because I do not need to use 7, okay? I can use other numbers. Use 3, use 5. Yeah. Here I just pick 7. Pick 7, okay? But the 7 does not have any significance, okay? The only information we use in the 7 is greater than 1, okay? If it's greater than 1, then we can put here. Okay? I just want to exclude n equals 1 case, okay? Yeah. So I put this condition. All right. So then, can you imagine you can find some special input? Then you can arrange them such that none of them is in place. That's the meaning. Okay? If you can find one example, then you can get the answer. Yeah. That's the number 5. Number 9 is similar, right? Yeah. Yeah, similar understanding in place, but this time only 2 elements are in place. The remaining n minus 2. Yeah, this time I use n greater than 1. Okay, yeah. Yeah. The remaining n minus 2 elements are not in place. Okay, yeah. All right. So this time, the experiment you use in 5, can you modify it? Definitely you cannot use the same example, right? But you need to modify it slightly. Yeah. Then you can get number 9. Okay? Yeah. That's the hint for these 2 questions. Sometimes you need to create some special examples like these 2 questions. Yeah. In math, we call it counterexamples. Yeah. But here may not be counterexamples. The examples that satisfy certain conditions. Making examples. Yeah. All right. Next. Question number 21. Given 19 elements, it is known that x sub 10, this one, is not in place. You know the meaning. Okay? So if we sort it, you have to move x10. Okay? When you sort this whole array, yeah, because the original location of x10 will change if you sort it. Okay? It's not in place. You have to move it. The destination location is different from the original location. Yeah. So what is the maximum number of inversions? You know the inversions, right? So here you need the first thing, you need to understand the inversion concept. That is AI, AJ, a pair of, you look at a pair of elements in the array with I less than j and AI greater than AJ. Okay? That's the inversion concept. Yeah. So the original location, AIAJ, you know, yeah, so the locations, AI appears before AJ, okay, that order, there is the order, okay, subscript order, index order, but their values just opposite the index order, that value different, out of order. Yeah. If the value still in order, then no inversion. Okay? No inversion. Yeah. But now the value is opposite, out of order. So you need to fix it. So it's an inversion. In order to solve it, you need to remove this inversion, right? You need to fix that inversion. Yeah. For example, by swap operation, you fix it. You swap these two elements. All right. All right, so that's the review of this concept. Yeah. Because many students, you know, I noticed, so they do not understand this concept. Then, after that, now let me give you the hint. Strategy. So problem solving strategy. Okay. In our problem solving, there is a general strategy we apply to solve problem. All right, yeah. 2 steps. We use 2 steps. The first step, find and approximate. And easy solution. Okay? So we do not, because sometimes the problem is relatively hard. It is hard to find a solution. Okay? So then we modify the problem slightly. So this way we modify the problem. Modify the problem to make it easier. Right? Yeah. So now we solve this easier version of that modified problem. So the solution we treat it as an approximate solution, not the same solution, approximate solution. The second step, fix the gap. Yeah, there must be a gap, right? This approximate solution and the final solution, there must be some gap. So we fix that gap part. Okay? Yeah. Yeah, fix the gap. Okay? Yeah. We hope that gap is small. So if it's small, then it's not hard to fix. Okay? If the gap is large, then it's hard to fix. Yeah. So we want to make our approximation as close to the final solution as possible. Yeah. All right, so here, let's apply this strategy. The first step, we need to modify the given problem to make it easier. How do we modify? Yeah. So how to modify? How to modify it? The first question. Let me give you the answer. Okay? Remove the condition. What condition? remove this condition. X sub 10 is not in place. Okay, remove this condition. Can you find a solution? Yeah. Given 19 elements, no further other conditions. What is the maximum number of inversions? Answer this question by this strategy. This problem solving strategy, very effective. Very effective. Okay? Yeah. Right. Then many students, let me tell you the error, common error. Many students, and when they answer this question, because here, when you need to look at the total number of inversions, large number of students, they only count adjacent inversions. Okay? Yeah. So here, I need to write down this sentence. You need to count the number of global inversions. The number of global inversions. Not only the adjacent inversion. Yeah. Because so many students just give me the adjacent inversions. 18, yeah. 19 elements, when you count the number of adjacent inversions, you get 18, right? Yeah, 18 adjacent pairs. Okay? So 18 possible inversions. All right. But count global, okay? Not adjacent. Two elements could be far away. Okay? Any two locations. All right? Yeah. Then the maximum number of inversions, you need to imagine for what input you get a maximum number of inversions. The input like this, okay? An array like this, descending order. So your input in the descending order. This kind of input, you will get the maximum number of inversions. Okay, so you can get a formula. Here 19, so you plug in 19. So n, so arbitrary n, you can have a formula, but here 19, n equals 19. All right. After that, so you find a solution, step 1. Then you put the condition back. After that, x0 not in place. You put that condition back. Okay, look at when the array is in descending order, x sub 10, is it in place? Descending order, is x10 in place? Think about that. Okay? Yes, it is in place. x10 in the middle, right? When you get a descending order, x10 also in the middle, right? Think about that. That's in place. Okay? Descending order, if you sort it, ascending order, you do not move x10, right? You get descending order, x10 in the middle, but when you sort it, ascending order, x10 stay in the same place, right? No change. That means x10 is in place. But our condition x10 not in place. You need to move. You need to make one move. The destination, x10, cannot stay in the middle. x10 has to go some other places. Okay? Think about that change. That change how much you need to modify your answer. In your step 1 answer, you have an answer, right? But you have to make that change. Moving X10 anywhere, just it cannot stay in that location. Okay? X10 can go anywhere, but not that location. How much you want to modify your answer from the step 1? That's the hint. Okay? Try to follow the idea. All right? Try to follow this idea. Let me look at the time I have. Yeah, 10 minutes. I have 2 questions to go. Yeah, but hints. Yeah, hints. I can control. So each one 5 minutes. All right. Number 22. Given 354 elements array, what is the minimum number of comparisons that you need to find element among top 6? Here, you need to do a lot of analysis work to understand the problem better, to view, to understand better. Yeah. So here, I recommend you use the result. Yeah. We have a problem. We solve a problem. Yeah. Finding the minimum. The problem, we solve it, right? And then we get optimal solution. N-1 comparisons. So you use the solution understanding from this problem. Yeah. So this is your reference problem. So you use the understanding of this problem to solve this one. Okay? Yeah. Because how do you connect? Actually, these 2 questions closely related in this one. Because what's the minimum? Minimum means top 1, right? Top 1. Okay? The value, the top 1 element, the bottom one. The minimum, yeah. Because finding the minimum, that you can change to maximum. Okay? Yeah. If you change to the maximum, the solution is similar, right? Maximum is top 1, right? Finding the maximum. Yeah. How many comparisons? Still N-1 comparisons. Change the minimum to maximum first. Yeah. All right. Yeah. What's the maximum? Top 1. Top 1 is the maximum. Okay? Yeah. But here, we change the top 1 to top 6. Okay? Yeah. And the top 1 maximum, we apply, how do we solve it? Apply the elimination method. Elimination method. How to eliminate? We eliminate the winner, right? The final winner, okay? The winner eliminates N-1 elements by comparisons. Yeah. So that's what we do from the finding the maximum. Okay? All right. So now, for a new question, so you follow the same logic. The same logic. Yeah. The winner, yeah. So for the winner of all the solution. Yeah. The solution. The element that is among top six. Yeah. A solution. Yeah, because we only have multiple solutions. a solution. Okay. So for this question, our understanding is a solution okay, should eliminate n minus 6, right? N minus 6, yeah, because if that particular element, solution element, is larger than n minus 6, then it must be in top 6, right? A solution should eliminate n minus 6 elements by comparisons. Because if you can do that, then that element must be among the top 6. Must be among the top 6. Okay? So result that one must be among the top 6. Okay? Yeah. That n equals 354. Okay? So you can change that n number. Yeah. The n number is not that important. Not important. Okay? The n number. Not important, what I mean is that you will change n number, your solution thinking is the same. Okay? The answer is different. But the thinking is the same. Analysis is the same. Logic is the same. So that's what I mean. Not important. You don't need to change your solution logic. Okay. Yeah. All right. Last question. Number 25. Another. Because here I want to practice elimination method. Another one, you need to apply the elimination method. Because that method is very important. So I want you to practice many, many times in your thinking. All right. So here, two given arrays are ordered arrays. The first ordered ascending order, second ordered ascending order, right? So our goal, so when we put them together, we need to find the median. We look at all 11 elements, and we want to find out that the median element. Yeah, we assume they're distinct. All elements distinct. Okay. Yeah. All right. So now you know the median one, because you have 11 locations, right? Yeah. If you sort all of them, locations. If you sort it, so here I put if sort all your data. Okay, yeah, all your data. So the median is here, median. But median is here in the middle, the one in the middle. So your view, you adjust your view. You have two different views. One view from left. So you look at the median from the left. It's 6th smallest. Another view from the right. Okay? From the right. then it's sixth largest. Yeah, so that's the property of the median. Okay, all right. Then, given the condition x3 less than b3, a3 less than b3, a3 less than b3, then how many elements can be eliminated? So after this condition, okay, how many elements can be eliminated for the median? Okay? Because what criteria? If it cannot be the median, then you eliminate it, right? So that's the for the median. From two sides, okay? Yeah. Because you look at from the left, from the from both the left and the right. Sides, okay? How many? Yeah. For example, yeah, I'll just give you an example. Because the median, you know, the median should be, you count the sixth one from the left. But if you can see some element is already greater than 6 elements, one particular element, if it is greater than 6 elements, then it cannot be the median, right? Because from the given condition, you can see one particular element is already greater than 6 other elements. How can it be the median? How can it be the sixth one? Sixth smallest one? It cannot. So you can eliminate it, right? So use this logic to do the eliminations as much as you can. Both from the left, after you complete left view, then you change your view, the right view, okay? Right side view, left side view, right side view, to do the maximum elimination. All right? That's the first round. Then, because you reduce number of elements, then you do comparison, second round, third round, until you find the final median. Our goal, how many comparisons, how many more comparisons to find the final median? Your goal, you need to find the final median. Okay? All right, so that's the, yeah. So we'll have to stop right here. Yeah. So, the end.